All right, so how you guys doing today? Good.
Good.
You guys had a lunch?
Not yet.
Not yet. Oh, me neither. I'm so kind of hungry, but we'll get there soon because we're done in an hour. Okay. So hopefully you can get a lunch if you didn't get one. Here you go. So last time we talked about how we're gonna name the compounds. We learned about how we're gonna name the ionic compounds and the molecular compounds. Okay. And also some acids. So then one that donates the hydrogen cation, we can say proton. We can name it in two different ways, binary, and also some oxy acid with some polyatomic anions. Okay. So this is what we did last time, and the last one that we're gonna try to name is what we call organic compounds. Compounds. So organic compounds is mainly made of the carbon, and hydrogen. So if you have a certain compounds, obviously carbon and hydrogen makes the not just molecule but also the compound. If it's mainly just about carbon and hydrogen, we can definitely call that compound as one organic compound over there. So I actually give you one quick names for the organic compounds, but we have three different parts of the name of the organic compounds. So the first one is a locant. The next one is a prefix. Then the next one is a base. And the last one is a suffix. So, but I'm not going to go over these too much though, because the prefix is for some additional group that attach to your base. So this base simply means, so once again, try to remember organic compounds is carbon and hydrogen, so forth, okay? So this is the way you can find the longest possible carbon and carbon chain, okay? And then if there is any additional group attached to your base, which is longest carbon chain, that is going to be your prefix. So locant is simply meaning, this is information about where this prefix, additional groups are attached to on your base. Okay, so these two are kind of free-for-all groups on your base. So this is kind of a first job you need to do when you try to name the compounds, organic compound in here. This one, just you need to know three things. It is going to be A-N-E, and E-N-E, and Y-N-E. Okay? So we're gonna get to this one real soon. But this is a kind of a brief idea how we're gonna name the organic compounds. But I'm not gonna do much of these two, but maybe more on these two. So those are kind of additional information on organic compounds. So let me show you some example over here. So what I mean by the longest carbon chain, and you're gonna also try to find out the numbers of carbons in your longest carbon chain. So if I give you this three carbons kind of chemically bonded to each other, like in a linear shape, okay? And then what you can say is each carbon, if you look at the carbon in the periodic table, it's actually in the group 4, okay? So meaning it's the first and second and third and fourth, okay? So that has the carbon is group 4 elements. Okay? Group 4 elements. So I just want you to remember this one. If it's group 1, it has the 1 valence electron. If it's group 2, it has a 2 valence electron. Group 3, 3 and 4 and go on, it ends at the last column that is group 8. So if you look at the carbon, you're actually going to skip the D block at the bottom, in the middle bottom. So it's first, second, and third, and fourth. So that's why I'm calling this carbon as group 4 elements. So it has a 4 valence electron. So I hope you guys remember this from the chapter 1, that whenever you look at the atom, it has like a nucleus at the center, and most of the parts of your atom is empty space. Most of the parts is just empty, and you just have a nucleus at the center. You have electrons moving around it. That's pretty much it for the atom. But obviously, carbon has a lot of numbers of electrons over there and moving, but they're only going to moving in certain orbits based on the Bohr's model. Later in organic chemistry, we're going to learn about orbitals as well. So we can look at it more in modern physics and 3-dimensional space. But for now, if you put it in the 2D like a model, like in the Bohr's model, the one on the most outer orbits, or the most outer shell, we can say, there's the one that it has the valence electron. So the one on the inside, we call them inner electron. But for your chemical bonds between other elements or the same elements, only electron they can use is the one on the most outer shell. Those are what we mean by valence electron. This is how we name it. Okay? So this is the only electrons that they can use for bonding. They cannot use the one inside. If you think about this is a proton and neutron, right? So obviously it's a positive part charge at the center, and electrons are obviously negatively charged. Okay? So if you think about, if you want to do something with the electrons, the electrons that are close to your nucleus will be really strongly held to each other. So it cannot be easily used, but the one on the most outer shell will be easier for them to arrange, like they move it around. So those are the only ones that can possibly use for making chemical bonds. So carbon has 4 valence electron over here, and hydrogen is group 1. So meaning hydrogen only has 1 valence electron over here. And then what they do in this type of chemical bonding is that they try to find a really good local space where they can share the electron together. So one from the hydrogen, one from the carbon here. So a pair of electrons are kind of moving in the same similar space between hydrogen and carbon. So literally, this will make chemical bond we call covalent bond. So it's just kind of makes sense if you just look at it that way. They share their each valence electron from carbon and hydrogen in one small space together. So this is how they make a bond there. So co simply means together, right? Carbon and hydrogen share the electron together. But this is not just electron, but valence electron. So you make it more an adjective form of valence, meaning valent, right? So this is why we call this covalent bond. This is the chemical bond they make by just simply sharing their each valence electron in the certain same common ground. So this is covalent. Makes sense, right? Okay. So, but the thing is, hydrogen only have 1, but carbon has 4. Okay, so that means carbon can have at max 4 bonding. Okay, so this carbon has 3 hydrogen. That's why, because it has 1, 2, 3, 4. Okay, this carbon has 1, 2, so we have only 2 hydrogen. Okay, because it has only 2 carbons are making bond to here. So 1, 2, 3, 4. 1, 2, 3, 4 as well. Okay. So we'll give you 3 carbons, and if you count the hydrogen on all other carbons, it's 8 right there. Okay. So this is the organic compound chemical formula we have by simply just filling this carbon with a hydrogen over here. Okay. We good, right? Okay. Perfect. So if that is the case, let's try to name this one. Okay. Let's try to name this one. So if we have a C3H8, so in this case, obviously, the longest possible carbon-carbon chain is right there. We have 3 carbon in a chain. That's pretty much it. So you just try to count the numbers of carbon. 1, 2, 3. So you have 3 carbons in this carbon chain, longest possible carbon chain, right? Then you just need to know this one. So you'll find the table in the textbook. It says the math prop build 10 hex hept oct non and dig. Okay. So it's just the meaning how many carbons are there. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So there's more name for the number that is bigger than 10, but you don't have to know. Is it the undecine, dodecine, icosine, cosine? You don't have to know. Just up to 10 should be just good enough for most of the chemical formula. So if that is the case, you find the 3 carbons in the carbon chain, and you just need to pick this number right there, this name, prop, right? Prop. And then if they're all made in single bond, you just need to put A and E at the end. So I told you about the suffix that you only know most of the organic compound is this one. So the A and E is when it has only a single bond. So the single bond simply means there's just one pair of electron share in each bond. That's the single bond. If there's a double bond, we put E and E instead of A and E. If it's the triple bond, meaning we put the Y and E. So if there's 3 pairs of electron share in the same space, that's a triple bond. 2 pairs of electron share in here, it'll be double bond, and 1 is a single bond over here. Okay. So if you do have some double or triple bond, you change that the suffix name as E and E or Y and E. But for now, it's all single bond. So it's just the propane. That's it. You just get that name from the table, prop, which is 3, and all single bond, it's just the 1 pair of electron making bond for each bond on the carbon, hydrogen. So we put A and E, so A and E is propane. So if we have a double bond, meaning you're going to have not 1 pair, 2 pair, 2 pair of electrons. It's like this. So you have 2 valence electrons from this carbon and this carbon making a bond. So not 1 pair, but 2 pairs of electrons making even stronger bond between these 2 carbons. In that case, we're gonna call this propene. This is a double bond here. That's why you're losing 2 hydrogen from the A and E version, because they used another pair of electrons to make the double bond to the carbon-carbon, not the carbon to hydrogen. So that makes, if you have a triple bond, which is even stronger than double bond. So now you have a 3 pair of electrons. So now you lose the two other hydrogens as well on here from the E and E. So that makes so A and E is this one, E and E is this one. Now you have Y and E. So you see the numbers of the hydrogen are decreased over you go from higher and higher order of the
So
bonding.
carbon would stay the same no matter what?
Carbon, yeah, carbon. I mean, I made it that way. Yes.
Okay.
So you can also change the number of the carbon as long as you keep just 4 valence electron each. That's a very good question. I just made it that way so we can actually see the loss of the numbers of hydrogen at the higher and higher bond order. That's so if that is the case, we just also, not E and E now, will be Y and E. This is a propyl. That's it. Okay? So maybe I'll give you one example here. You can try this one. You have instead of 3, well now we have a 4. So I'm gonna fill this one with the hydrogen. Okay. And I'll tell you the trick. If you have 4 carbons, okay, and you don't have any double or triple bond here, I just know that it's already 10. I didn't even count it. I just know there's 10. Because we follow CN H2N plus 2 rule. So if there's no double or triple bond, if you know how many carbons are there in organic compounds, because the N stands for the numbers of carbon, which is 4, right? But then automatically, if they're all single bonded, the hydrogen will be just 2N plus 2, meaning 2 times 4 plus 2. So 2, this is 4, so this is 2 times 4 plus 2, that makes 10. So I don't even have to count the numbers of hydrogen if I just remember this N, CN, H2N plus 2. Okay? So if that is the case, you just need to know what? Count the carbon in the carbon chain, which is 4, which is but. They're all single bond, so it will be butane. So that's the name of the disorganic compound. So let's do this again. So let's make it, just get rid of 2 hydrogen, make it double bond, will become butene. Okay, butene, right? Butene. And let's try to get rid of the other 2. Triple bond, and it will be butyne. Perfect. Okay. Butyne. That's it. Okay. So so if it's all single bond, you can have a CN H2N plus 2. Double. If there's one double bond, CN H2N. Okay. If there's one triple bond, you can say CN H2N minus 2. I think this is easier for you to remember, so you can just count the hydrogen and carbon so easy. But you can also remember those, and you eventually know how many hydrogen and carbon anyway. So either way, it's fine. So far, so good. So far, so good. Perfect. You guys are doing great so far. So maybe can you guys maybe this is a PENT, okay? So maybe. If I just give you this one, okay, what might be the name of this one? Do you think? It's a PNET. There's a 5 in the carbon chain, so it'll be, and all is all single bond, so it'll be this one. So it'll be pentane. Perfect. You got it. You got it. So that's it really. If there's a double bond, it will be pentene. If there's a triple bond, pentyne. Yeah, that's pretty much it. So I think only job you really have to do is just this one. I think it would be great if you can just memorize them all. I'll think about it. I may just put the table on the exam so you don't have to memorize it. You just need to know how to use it. But I think still, any chemistry major here? No? Oh, okay. So I'll maybe just put the table on the exam so you don't have to memorize it. But I think it would be just great if you just can memorize it. But Anyway, so this is a kind of a thing we need to do for naming organic compounds. Like I said, we have another more complicated structure. We can name with the prefix and the locant, but I think we're quite happy here for second one. Okay. Sounds good? Okay. So but if you want to know, you can always stop by my office. I can tell you more about the nomenclature for organic compounds. Okay. Let me tell you one thing over here. Do you know do you like snacks, chips, right? So if you buy those things in the Walmart or in some grocery store, you always have some information on the back. It says nutrition fact. You guys know that, right? And then what they really need to say by law is the contents, how much they have a trans fat. You guys seen this so many times on the nutrient fact, right? Okay, this is not going to be in the exam, just for your information. So just have a little time to enjoy the chemical knowledge from the real life. So the trans fat is simply, if you think about the fat, like you know the fat, right? Fat in your food. The main parts of the fat is just the carbon, hydrogen, 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 carbon, hydrogen. What we just discussed, propane, butane, but it's just longer version. It's all carbon chain, but they fully saturate with the hydrogen, meaning they're all single bond. All single bond, single bond, single bond. So there'll be maximum possible numbers of hydrogen are kind of surrounding this carbon here, which is the main parts of the fat that you can easily find in the food. You have a glyceride head groups, but you don't need to know. But the main tail groups are made of just organic compounds. But it has a trans fat because whenever you have a double bond here, the funny thing, once again, this won't be an exam, just for your information. Whenever you have a double bond, the single bond is interesting. You can actually rotate it. Okay? You can rotate easily. But if there's a double bond, actually they have either way. It's what we call transform, and this is what we call cis form. Okay. And in this case, you cannot rotate the double bond, so they don't have a freedom to make a rotation on it. So whenever they either have a trans or cis, they cannot change the shape. For example, if you have a carbon looks like this one, they can go even this way too by just rotating it. But this one, it cannot. So I'm saying, why is it so important here to know about double bond cannot rotate it, but single bond can be easily rotated. If you think about this one in the space, like I said, there's all mainly single bond, right? So there's single bond, carbon, 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 carbon here. So if that is the case, they can always rotate, even though they come onto in this side, maybe, they can rotate it, so they come more perfect fit on this too. Okay? So those are the one without double bond or triple bond can be easily stacked them each other, meaning they're going to have a very small space between them. They will make this fat can be easily solidified, like butter. If you look at the animal butter, at the room temperature, it can be easily solidified. It just become, once it's a liquid at the heat, but when it's cooled down, it will be liquefied. But, like I said, if you have a double bond in your organic compound structure of the fat, maybe you have this one, which is a trans. This one is a cis. Okay? So in this case, if you try to mix these two or other just the regular single bonded the organic molecule, or we can say fat molecule, this cannot be well stacked together, right? Because this structure cannot rotate. So you cannot rotate to make this one so they can be more stacked well, but they cannot. So they have a certain inefficient way to make the spacing for their volume. So meaning, you guys remember this? If there is not much of space or distance among the molecule or the atom, it will become solid. But if there's a bit bigger, longer distance, it will become what? Liquid. Remember this, right? If it's even bigger, it will become gas, but which is almost impossible at room temperature for most molecules. Anyway, so if this is the case, if you have some molecule in your fat, that type of fat that has a cis form in your double bonding, they cannot be easily solidified. So if you look at some healthy vegetable oil, they're usually in liquid and room temperature. So it is better. It is better than other butter or animal fat because they cannot be easily solidified. If it's happening in your blood vessel, it will cause heart problem. But vegetable or healthy oil will not, because it will be still liquid in your blood vessel. And also, the organic compounds can be easily kind of interacting each other. So if you're eating a lot of good oil that has a very healthy form, they can actually also clean up your unhealthy fat stack on your blood vessel as well too, because they kind of mix together and float away in the bloodstream. So this is why it's so important to know how much of those two different types of the fat in your food to know. And now you wonder why trans matter then, because it has a double bond. Because trans is also do the same thing what it does for the other. Because the trans is the way it looks, so you don't have to rotate it, they can stack it well. This is usually happen in the processing in the other food industry. So if it is too much, they also cause a lot of heart problem too. So that is why, by law, they need to indicate how much trans fat they're putting into their food, they're sending to the customer. But once again, this will not be in the exam. But just good to know. Why does it matter? Why you need to know about this? Because most of the sugar, fat, and some of protein is mostly organic compounds. So I'll move on. Okay. So just a quick tip for your real life. They use the chemical knowledge. So we're pretty much done with the chapter 2 now. So now we're gonna enter into the first part of the chapter 3. So chapter 3 is about all reactions, but the chemical reactions. Okay, chemical reactions. So chemical reactions is simply there's the two different compounds or the elements will interacting each other, making a completely new product. So meaning if you go from A plus B, you probably have some other components or one product or two or three, you name it, but it has to be different from the initial one. So we normally put the one that we start with in the chemical reaction on the left side of the equation here. So we always put those one on the left is the starting material, and the one on the right is the product. Okay, so we have a certain name for it. That is what we call. So this is what we're going to react with, right? So this is why we call this reactant. Because they're going to do the reaction. So this is what we're starting with. So we call them reactants here. And those two are obviously outcome of the reaction. So we call them products. This is what we made from the chemical reactions. Okay. Okay. So this is kind of a basic form of the chemical reaction. The one on the left is reactants, one on the right are the products. And you can always assume that left to the right is the way that chemical reaction goes. Later you're gonna learn about the equilibrium in Gen Chem 2 and so on. In that case, you're gonna learn about the reverse reaction, which will not do much on Gen Chem 1. But the bottom line is you can always put the one on the left is reactants and the right is product. So you can always think the reaction goes from left to the right in the normal situation. Okay, makes sense, right? Okay, perfect. So I'll give you one example here. Since we learned about the organic compounds, let's try to have some fun with the organic compounds. So if I give you CH4, which is methane, because it has only one carbon. They're all single bond to the hydrogens of methane, and we can try to burn this methane with the oxygen, right? Obviously, we need some oxygen to make some combustion reaction. So, if you're burning something, we call this combustion reaction. And then most of the time, if it's really ideally completely a full reacted reaction, it's only going to give you carbon dioxide and water. This is what we find out by doing a lot of experience with the combustion reaction of the organic compounds. Okay, so if you look at this one over here, you're also going to see. So if I give you this and ask you what are the reactants, what are the products, you need to tell me those are our reactants, those are our product. Okay, that's what you need to know about it. So anyway, and then there's a couple more things. So those are the ones that we call chemical formula. This will tell you how many of that element or the other are chemical bound to each other to make that molecule or compound. So obviously it has one carbon and four hydrogen, two oxygen, one carbon, two oxygen, two hydrogen, one oxygen, so forth. Okay, so this is chemical formula. And also it has some small, like subscribed parentheses on each reactants and the products. It indicates a physical status. So we normally put this the phases of matter. So you can put gas phase, we put G, this gas. If it's a liquid, we just put L. Okay? If it's in the solid phase, we put S. Okay? So you normally see those things to indicate what physical status it has when we did the chemical reactions, and when it had an outcome, what phase of the matter it was in your products as well. Okay, so in this case, there's a couple things you actually have to do. Think about is the you guys remember the separate rule I told you, and I think it was last week that about the mass conservation rule. You guys remember that, right? The mass, because so meaning. If you find the one carbon here, okay, you should also find the one carbon here as well. Carbon just cannot disappear during the reactions or appear. It's just impossible. That's the mass conservation rule. And the proportion rule is the combination should be always kept the same for the same compound. So meaning you need to balance. You need to balance the equation, meaning left to the right. So numbers of carbons, numbers of hydrogen, and we also have oxygen, right? Numbers of oxygen should be same on the left, on the right. So this is what we need to do now. Okay. So if you think about this one, only carbon. The only place where you can find the carbon on the left side is methane, right? Okay, so if you have methane over here, this oxygen does not have carbon here, but the methane does. But you have a one over here, okay? And if you look at the right side, you also have only one compound that has carbon, that is carbon dioxide. So let's just start with a 1 and 1. So if you put 1 over there, meaning there will be one methane. You can also put 1 on this one, because this is where you can also find the carbon on the right side. And those number is what we call coefficient number, meaning just how many numbers of that and that will be there on the reactions. Okay, but we can start with always 1, which will be the simplest number we can try out. So maybe it has 1 here, but if you look at the methane, it is only source also for hydrogen, because it does not have a hydrogen here. So if you have indeed 1 methane, you should have at least 4 hydrogen on the other side as well. Because this is the minimum number you can try, but it has the 4 hydrogen on the 1 methane. But if you look at this one here, this water has only 2 hydrogen, perfect. So in that case, you need to put at least 2, because this is the minimum possible number for methane that gives already 4. right? Then each water molecule has only 2 hydrogen. So minimum number you can try for water is actually not 1 but 2. Because so you can make a 4 hydrogen as well here, which is 2 times 2 is 4. Makes sense, right? Perfect. So now we're kind of happy now because we know there'll be 1 carbon here, 1 carbon here, and 4 hydrogen here, 4 hydrogen here, and now we're getting to oxygen. Okay, let's get this number. Okay, so if that is the case, what you can do is 1 carbon dioxide has 2 oxygen here already. 1, and you have a 2 water molecule, but each water molecule has 1 oxygen, but there are 2. So 2 times 1 is still 2. So here 2 in total on the right side at this moment 4. Perfect. 4. Okay.
Add 2 to that.
Perfect. Absolutely, yes. So you can have 2 times 2, that makes 4 oxygen on the left side as well. It's perfect. That's the perfect right answer. So now, if you're done with the filling those numbers in front of each reactants and the products, that is what we mean by balancing. Balancing means the one without the coefficient number, so it's not balanced. So we call that incomplete chemical reaction equations. And once you balance those numbers of each element you see on left and right, now you can have a fully complete chemical reaction equation. Makes sense, right? Good, perfect. I think you guys think so, Chris. Okay, let's give you one more then. I can give you the ion compound one, but maybe we can do it Wednesday because we only have 4 minutes because we can try a little more. But anyway, so let's try to do maybe propane. Okay, propane. Okay, so propane over here, we have propane. And we try to also combust with the oxygen, obviously. And we already just memorized there will be only carbon dioxide and water. Okay. So the do you know why? Unfortunately, we have in case of the fire. Do you know what's the instruction you says? Is that you have to crawl on the floor, right? Because this is only happening when it's fully complete, meaning those carbon can catch all the 2 oxygen on it. But whenever carbon only catch the 1 oxygen, which is possible, meaning incomplete combustion reaction, they become really, really toxic because the carbon monoxide is very unstable. Carbon dioxide is just fairly stable. So if you inhale the carbon monoxide into your body, what they do is they try to steal the oxygen from your body. That is why it is so toxic gas molecule. So this is why you have to kind of, but carbon monoxide is lighter than carbon dioxide, right? So that goes, relatively speaking, on the upper space than the down space. So that is why most of the incomplete smoke, do you see the smoke coming out from the building, right? They're always going forward, the upward, right? Not the downward, right? So this is why the instruction for in case of fire, unfortunately it happens, you need to crawl on the floor, covering your mouth. It will be much safer way to escape from the fire. Kind of makes sense, right? But this is for more like a complete, anyway. So if that is the case, we can also try to balance, which meaning you're gonna feel there's the coefficient number for each. So this is the only source of the carbon and hydrogen, so we can start with the 1 first, okay? Let's try 1 first, okay? Then they'll make 3 carbons at least on the left. So I'm gonna put 3 right here, okay? So 3. Because this is the only source of carbon on the right side. But even though you try 1, there has to be 3 for making 3 carbons on the right side as well, here. And that makes also 8 hydrogen at minimum. So this one has to be 4, right? 4 times 2? Yeah. Yeah, multiply, yes. Because each sorry, the water molecule has 2 hydrogen, but 1 propane has already 8. That's why if you have to have a minimum 4. So you can have also 8 hydrogen. All right. So now we're gonna look for the oxygen now. So you have Oh, you already got it. Yes. So 3 times 2 is 6. 4, yeah. So 10 is 35. Yeah. Wow, you guys so quick. I'm so impressed. That's it, really. Yeah. So this is a very easy another example you can try with one other example of organic compound combustion rate. So only thing you really need to know is the product will be carbon dioxide and water, and combustion reaction they need to have oxygen to be burned as a combustion reaction. So this makes quite easy, nice example about how we can balance the equations. Yeah.
Could you give us one more example?
One more example. Yes, absolutely. Real quick. Let's try to do maybe. This is a bit. This is ethane. Okay, let's try to do real quick. And then in this case, same here. So I'll try to start with 1 first. Okay, 1 here. And then you have to have how many maybe? 1 or 2. It already have a 2 carbon with 2. Oh, because the 1 ethane already has a 2 carbon here, right?
Yeah.
So each carbon dioxide has only 1. So at minimum it has to be 2. So you can have a 2 carbons in there. Then if you add a 1 ethane here, that makes this 3 water. So you can have also 3 times 2, 6 hydrogen here. 1 times 6 is 6 hydrogen over here as well, right? So here's the thing. Now you have 2 carbon dioxide and 3 water here. That meaning you have a 4 oxygen on here, but you have a 3 oxygen over here. So you have a 7 in total oxygen on the right side. The problem is your oxygen has to be diatomic molecule. So it's an odd number, can be easily divided by 2. So here's the one thing you can do is you can also do sometimes in the fractional number. So 7 over 2 times 2 is 7/2, right? So you can do 1, 3.5, 2, 3. That's okay. That is totally fine. But if you don't want to have a fractional number on your equation, okay, then what you can easily do is multiply each side by 2. Okay, so that makes 2C2H6, right, plus 7O2 make 4CO2, 6H2. Okay? Same. So this equation actually same thing, because we only double on the both sides. Like if you have a 1 equal to 1, if you multiply by 2 by 2, 2 equal to, it means the same thing, right? Same here. You can also do this if you don't mind with using fraction number, but you can also do in this way with the really nice whole number, integer number for each coefficient number, which looks kind of more nice. I don't know. So, but remember, those two mean the same thing anyway. It's not different. It's just the same, but just double by both sides.
So you got,
Mhm.
so you get 6 from the 3 and then 8
Mhm.
2, so that's 6. And then
So this one has 1, right? 1, so it'll be 2. So it'll be 2 times 2 is 4, right?
yeah.
And but the water molecule only has 1 oxygen, so it has 3 oxygen here. So 4 oxygen plus 3 is 7.
Oh, okay. I see.
Oh yeah, good. But yeah, so that's why we use this fraction number. If you don't want to do it, just multiply by 2, so you can have a really nice whole number for each coefficient. This might be a little bit trickier than previous 2, but let's do it. So I'll just stop here. Okay.